In the last segment, we said we'd look closely at the leader-seeking loop in STEP. Now that loop uses an iterator to go through all, getting all the other herd animals. Iterating, or looping through an array, or a list, or other collection of things is a common task, one you've probably written dozens of times in prior programs. So we're talking about a simple loop like the one right here. Now, an iterator is an object that represents such an ongoing loop-through process. It has member data that say where we are in the process, for instance, an array index, if the iterator is going through an array, or alternatively perhaps a node pointer if it's going through a linked list. The iterator has methods to step to the next element, the equivalent of I++, to get the element at the current point, the equivalent of array bracket I, for instance, and to check to see whether it's reached the end of the collection. For instance, the kind of check you would do with I is less than array.length. Now, collections that support iterators always provide some way of getting an iterator object that is kind of pointing to the start of the collection. And once you have an iterator object, you can use it to walk through the collection. Now, it is sensible to wonder why we would take such a simple process and turn it into an abstracted iterator object. There are very good reasons, and we'll talk much more about this in later segments. And we'll also look at a few simple implementations of iterators at that time. For now, let's concentrate on how iterator objects are used. Here's some example code. In Java, iterators are objects of the library class Iterator. And ArrayList's iterator method returns an iterator object pointing to the start of the array list. So this code here makes iter refer to an iterator object positioned at the start of all. Iterator has a method hasNext that determines if there are any objects in the collection that have not yet been fetched via the iterator. So this call remains true unless iter has reached the end of all. And then finally, iterator method next returns the current object in the collection and also advances it so that when you call next again, you'll get the next object after that, and so on. So right after the iterator is created, an iterator.next call returns the first object in the collection and also advances iter to the second object. And then another call will return the second object and advance iter to the third object, and so on. Now, question one, put that all together and see if you can figure out what this loop does. It's pretty obvious. Returning from a pause, well, it does essentially the same thing as looping through by hand with an I index. It iterates through all the items in all and prints them all out. Now, note in particular the absence of the third part, usually called the incrementer, in the for loop header. There is nothing after the second semicolon in the header. So question two, just to be sure you think it all the way through, why don't we put an iter.next call in the incrementer? Returning from a pause there. Well, the problem, of course, is several things really. First, if you just do an iter.next, it's going to take the returned object and drop it on the floor because you didn't assign it into anything. And also, if we do two iter nexts in the same loop, we're going to wind up skipping every other object as we go through each iteration of the loop. So we don't want to do that. Now, Java's iterator is, frankly, awkwardly designed because the next method gives you the next object and advances the iterator in one method call. So there's no way to say, just give me the current object and stay there till I tell you to advance. You have to make one call of next for each object and hang on to the result for as long as you need it. And another awkwardness. Next returns an object reference. This is consistent with the general behavior of ArrayList in that it's a heterogeneous collection of object references, right? So if we know the reference is really, say, a herd animal, then we have to downcast, like this. There. Okay, so that's a review of iterators, and it should now be clear that this loop here, for instance, will walk through all the herd animals in all, assigning each into leader as a candidate leader to consider. So then, how do we know if leader is really worth following? Well, first, it may already be following someone else. It might have a non-null myLeader. Let's look at the code here for herd animal at this point. So we don't want to follow herd animals that are already following somebody else. Don't want to follow other followers. So we adjust leader, in this case, so that we replace it with the animal it's following if leader.myLeader is not null. Right there. Now, we also don't want ourselves as a leader. So we check that leader is not equal to this. Question 3 here. How would leader become equal to this? Can that really happen? And returning from a pause there. Yeah, sure, it could happen. Array list all contains all the herd animals, right? This guy has everybody in it. We added ourselves to it in the constructor, just like everyone else. That, by the way, produced an interesting bug when I was writing this code. Now, finally, we call isGoodLeader, which does all other necessary checking to see if leader is worth following. And it returns true if so. And we'll have lots more on that in a moment. If leader finally passes muster on all these checks, then we make it our leader by assigning myLeader to that value. We also ask it via a call of addFollower to add us to its herd, so to speak, so it will update our location in lockstep with its own. And we'll have a closer look at the follower class in a bit. And then we finally tell anyone following us, if we were currently a leader, to instead follow the new leader via this call of handoff followers. Now, as I say, we'll cover add follower and handoff followers in a later segment as part of the whole leader-follower mechanism. But isGoodLeader needs some serious discussion first. So a glance at the implementation of isGoodLeader here shows something interesting. It has no code. And there's an abstract in its declaration right there. isGoodLeader is an abstract method. An abstract method provides no implementation. It's designed to be overridden in a derived class. In fact, it must be overridden in a derived class to be callable at all. Otherwise, it'd have no code. An abstract method says, in effect, there's no useful implementation for this in the base class. I'll leave it to derived classes to make up their minds and provide an implementation. There's no herd animal level rule for who's a good leader. Cow and horse will have their own rules. And we'll express these by overriding isGoodLeader, and herdAnimal.step will call their overrides polymorphically. An abstract method is useful when you have a larger method, like step, that calls out to smaller methods, like isGoodLeader, to do certain subtasks, and which smaller methods may be overridden to customize the method's behavior, e.g. adjusting the rules for good leaders. And question 4. Now, why did I repeat that mouthful again? Big class or big method calls smaller method gets overridden, when there's a perfectly good term for that concept. What term is that? Turning from a pause there, I just described the template method design pattern. Recall that I told you it would show up again. Stop, a step, and isGoodLeader follow a template method design pattern. So I should have said an abstract method is often useful in template method designs. Now, a reasonable question, by the way, might be, what happens if I just make a herd animal object and call its isGoodLeader method, the one with no code? Then what? Java's answer is, you can't make a herd animal object. The existence of even one abstract method in a class makes the class itself an abstract class. Scrolling to the top here, right there. That abstract keyword is required in the class declaration, as it is here in herd animal's case. Recall we said we'd get to that keyword in the last lecture segment. So why would you want a class that can't have any objects? For the sole sake of being a superclass. An abstract class's only purpose in life is to be someone else's superclass and to provide standard code for the subclass to use and or customize by overriding selected methods. Is this a common thing to do in object-oriented design? Absolutely yes. Indeed, as we'll shortly see, it's common to distill a class down to the point where every method is abstract, and the class only describes a bunch of methods with no code, leaving it to some subclass to override and provide actual meanings to them. Such a purely abstract class is termed an interface, and CodeWorlds uses several of them. We'll do much more with interfaces in the next few segments.